All right, welcome back. We are Game 3001 in the summer 2021 semester at George Brown, and it's week 2, part 1 of our broadcast. Welcome back to Game AI. So we're sitting at the week of May 17th. That's the week. We're talking about steering behaviors today. As we're going forward, you can see that one of the things that we have to talk about is the assignment 1 that is due next Sunday at midnight. So it's kind of coming upon us quite quickly. I released the assignment 1 details last week. And again, I just want to remind you that assignment 1 is due not this Sunday, but next Sunday. And of course, that's like right around the corner. It sounds like it's quite far away, but it's not. And there's quite a few details you have to go through with assignment 1. So again, if you haven't had a chance to even start, I would look at that if I were you. And again, this is where we sit. I've just included both the entire course calendar so you understand what's happening. Last week, what we talked about was we kind of did an intro to AI. We talked about the difference between weak versus strong AI. What was that? We also talked about general game AI and AI agents. And we did, through our labs, we did a tour of the assignment framework, which, by the way, I've upgraded lately just to include the latest version of IMGUI, which I'm going to talk about in lab, as well as I patched a couple of bugs that we had from last week. So I kind of did those kind of things. And you'll see more and more updates, I would say, before fall semester. So there's going to be other ones that are kind of come forward as well. Okay, but we're trying to always improve things so that way it's just easier for you to do your assignments and not worry necessarily about the framework itself. So that's kind of what we talked about last week. We did also talk about what IMGUI is, an immediate mode UI. That's the paradigm where you can actually change the buttons and inputs so that you can do better utility, modifications or debugging with your code in real time. So that's what that does for us. And we also talked in detail about version control using Git and GitHub. So different than Perforce that you're using with our friend Philip. Okay, so that's kind of the stuff that we talked about last week. So what are we doing this week? This week, we're going to be talking about autonomous character movement, kinematics, an intro to steering behaviors, including the following: seek, flee, arrive, and wander. And what's due is Lab 2, which is going to be this Sunday at midnight. I've released Lab 2, and we'll do that together during our lab period. And then assignment 1, like I said, which is an individual assignment, is due next Sunday at midnight. I just wanted to mention it there because it seems like it's far away, but it's not. All right, so that's kind of the structure of what we're talking about today. Let's get into movement in the AI model. So really, when we think about it, without movement, we don't really have AI at all. I mean, unless you have some kind of tower defense game where you're firing with some kind of a tower that's not moving at all. But still you have movement because you have bullets that are coming at the player, right? So anything like that requires some kind of movement. And the movement we're going to be talking about this semester is going to lead us into more complex movement patterns next semester when we talk, we're working with physics. And that's kind of, this kind of course leads into that one. The stuff that we're talking about this week is going to be very relevant to the stuff we're going to be speaking about in the fall. So let's talk about that. Really, I mean, we use some kind of movement algorithm. And we talked about what algorithms are, which is a set of instructions that usually are replicatable or reusable, if you will, right? We usually put them inside of a function, and it doesn't really require decision-making at all, right? It's just moving, right? An object. So again, when it comes to moving a player, we have to think about how the player moves. And there's different movement patterns we're going to be discussing today. So one thing that we always know is that there is something called a current position we're going to be talking about, and some other possible physical attributes like velocity, some kind of maneuverability. That's a property that the player's game object might have, as an example, as well as mass and so on. and you can kind of attach these kinds of properties to your autonomous character, which is what we're talking about here, not necessarily the player. Okay, and movement takes these properties and then it applies these properties as, I would say, more like advantages and disadvantages to the player or to the autonomous character's movement ability. So, example, if I had a low maneuverability, let's say, for example, I couldn't move or couldn't turn or turn rate, something like that, then it would take longer for me to turn. The autonomous character we're talking about, the AI, compared to a higher maneuverability, right? So that's kind of when you create a loadout of enemies, sometimes what we do is we give them abilities, just like maybe in Dungeons and Dragons or other role-playing games, we give characters abilities like strength and endurance and those kind of things. And so here we do the same thing with our autonomous characters. So again, the structure looks like this. We have some kind of movement request. Maybe we have some kind of new velocity that we want to attain for the autonomous character, or some kind of forces to apply. Let's say we push the autonomous character with a force, and then the movement request kind of hits the player or the character, and then it changes the position, the current position, based on the movement algorithm that we're going to give the character. That's typically how it goes. Okay. And again, we'll talk more about how we're going to implement this in lab. So really, we need, again, a couple of things. We need the position of the autonomous character, and in this case, when we say the enemy to chase, most often it's the player. The player is the one that's the target for the most part. Sometimes also we might have an obstacle or some kind of wall, and we also have to think about collision detection. So we're going to do in this course some basic collision detection. And what we're going to be doing is we're going to expand that when we get into physics, which is going to be next semester. So in different kinds of collision detection algorithms. For this course, we're going to keep it simple because all we care about is the basics. Do we collide? Do we not collide? But in terms of collision detection, that is a topic that can be very deep. And there's different methodologies that we can use that we're going to be talking about next semester. So again, there's two types of movement, kinematic and dynamic. Let's talk about kinematic for a second. So again, a lot of times autonomous characters in older games, they had a few things: stationary speed, running speed, maybe walking speed. And then kinematic movement doesn't take into account anything like acceleration or deceleration. It's like instant on. That's what kinematic speed is like. Okay, so there is no acceleration or deceleration with kinematics. The output of kinematic movement is just a direction to go towards, whereas dynamic movement takes account other motion. For example, acceleration, deceleration. It's more realistic, and it makes it more immersive for the character to use dynamic movement. We'll be talking about both types of movements over these next 2 weeks, this week and next week. We also going to talk a little bit about our coordinate space. And we've talked about it a little bit with you guys in your fundamentals courses. So in game fundamentals, we might have talked about things like 2D space. How does that work? And in 3D space, 3D coordinate systems. So of course, in our game, in our framework, we're going to be using a 2D coordinate space, so X and Y directions. Sometimes it's X and Z, depending on the game framework. For example, in Unity, it might be X and Z, or something like that if you're going across, kind of the ground plane. But here, for the most part, it's usually X and Y. Most of our games nowadays, they're 3D and they use 3 dimensions. And a lot of times the y-axis is up. Sometimes we also have the z-axis up, especially when it comes to, kind of structures that we use, for example, in Blender. And I'm just going to pull up Blender for a second. Blender is one of our creational tools that we use to make 3D graphics. And one day when my Blender kicks off, then I can show you what I'm talking about. And I'll wait for that to come up. and I'll come back to it. It's what happens when you're broadcasting live, and you're broadcasting live and live, like 3 times. So I'll get back to Blender in a sec. So again, in addition to these things, as an example, we care about what the where the object is facing. So what the orientation value is of the object. So object facing is important too, because a lot of times it's more realistic for the object to go in the direction that it's facing, as opposed to go kind of, to slip sideways, as an example. And this is great. My Blender's still not responding. It's amazing. And this happens sometimes when I'm live. It's really bizarre. But anywho ways, let's continue. I was going to show you something, but it's okay. So a lot of times what we have is some kind of angle, from a reference axis. And the reference axis is usually, if I'm pointing to the right, so if I'm looking to the right of my screen, towards the east, as an example, usually that is an angle of 0 degrees. And as we rotate to the left, and this is depending on the framework, of course, some frameworks is the other way around. As we rotate to the left, we actually go in 90 degrees to the left. Sometimes it's a negative 90, sometimes it's a positive 90, depending on the framework. So we'll talk about that. So this counterclockwise angle usually is represented in the in radians. Usually that's what we do. And so when we kind of change direction, which is what we're going to have to talk about today, we have to convert our angle in radians to degrees. And we'll talk about that in our framework. So again, this is kind of a high-level view of it. One thing to note is the formula for degrees to radians is 1 radian is a degree multiplied by pi over 180, and 1 degree is a radian multiplied by 180 over pi. So those things are built into our framework, rad to deg and deg to rad. We have those kind of macros that are built in there, so it's easy for us to use. A lot of this, what we do is there in the book that we've referenced, they use something called the static struct that holds the position and orientation of our movement. But we saw last week that we don't use static structs at all. We use actually a little bit of a component called the transform. And the transform not only holds our position and rotation, but also holds our scale. So that's kind of something that we have in our framework. Sometimes also we refer to something called 2.5D movement, where we use an orthographic kind of structure. It looks like we're moving kind of into the screen, but actually it's not. It's just an illusion. Sometimes we allow characters to slip into the Z direction, kind of in a faux 3D kind of environment as well. And that's kind of what 2.5D looks like. We can also make our sprites look like they're 3D, but actually they're only 2D in terms of the way they cast a false shadow and a bunch of other stuff. So these are things we can do from an effect perspective, and it can affect the way our movement will look realistic or not. Okay, so that's kind of 2.5D movement. So when it comes to orientation, a lot of times, and by the way, guys, this is where math really, really helps with game development. We use vector coordinates, as an example when it comes to the direction of our movement. And a lot of times it's this idea of rise over run or sine over cosine, which is kind of tangent, right? Tangent to the curve. And what we do is we take the angle and we multiply it by sine for the y-axis. And we take the angle and we multiply it by cos for the x-axis. Typically the sine is associated with the y-axis, and typically cos or cosine is related to the x-axis. And we'll see that as we go forward. When we kind of change directions, we want to calculate everything in terms of triangles that we're going to be using when we're moving across the screen, right? And why triangles? Because if you think about this, right? If I march along let's just use a drawing board here for a second, right? So let's suppose I have a spaceship, and my spaceship is my little square, and I have a target and my target is a kind of circle, and I want to move my spaceship towards my target. In this particular case, you can see that clearly all we're going to do is move to the right? So it's not a big deal. But what if, and I'm just going to put it out there, it's not quite like that. My spaceship is actually down here. How do I move to that location there? Well, we're going to move in kind of a diagonal. It's going to look like it's moving in a diagonal, but really what's happening, we can break the components of movement, X and Y, down separately. So we're going to march across, kind of stuff along the X-axis, right, first, and then we're going to march up along the Y-axis. So it's going to be X and then Y, and then X and then Y. It's going to be, of course, simultaneous, so it's going to look like this, right? But we're still going to use these little angles. And if you look at what I'm doing, I'm making kind of like two sides of a triangle when I do that. So what I mean is, if we move to the right this way, move to the right this way, and then I move up this way, right? Because I'm going to go at an angle. I want to go in this particular angle here. Then I'm making a triangle, right? So what I care about then is the component on the X-axis that I'm going to be moving my character, right? So this is the X-axis. And how many pixels I'm going to go on the Y-axis. So both those two things. So there's X and Y. I know this is math, and people, they're like, do I really need to know math when I'm a game developer? Absolutely. Yeah, that's kind of the way it's going to go, right? So X-axis on this side, Y-axis up here, and then you have this hypotenuse, which is, again, we're using an example of Pythagorean theorem when we're moving our object in this way. And what we also have is an angle. See if I can draw the angle properly with this little program. Yeah, so you have an angle that kind of moves out. Okay, that was bad. Let's see if I can use this one instead. Okay, so yeah. And that's even worse. Haha. But anyways, the idea is that the angle is like this, and that angle in here is, we call that theta. So when we want to march, X number of pixels on the X-axis, as an example, then we want to multiply that by cos and multiplied by cos of the angle, which is theta. So again, the formula would be something like this: X, right, and then multiplied by cos theta. I'm just going to type theta because I don't have a theta symbol, right, where theta is the angle, right? So that is movement across the X-axis. So X-axis movement. And that is like your next pixel across the X-axis. That's what you're going to see a lot, right? So X-axis is you're going to take the angle. This is theta. Let's mark that as well. So we have that as an example. And that angle theta, right, is something that we're going to be using, whatever that is. Whatever, we're just mainly making it at theta. You can make anything you want in there, whatever a symbol you want to use. But at the end of the day, that is kind of the formula for the X-axis. So similarly, then the Y-axis, like we said, is equal to Y multiplied by sine times the angle theta, right? And that would be how many pixels across the Y-axis, all right, that you want to march across, right? And then, of course, you can multiply these two things by the speed of the object. If you just do this, it's 1 pixel per pixel, right? 1 pixel at a time. But, maybe the ship is going to move more than 1 pixel per frame, right? So you're probably going to multiply this by some kind of speed and maybe even times delta time. And the reason why you want to multiply it by delta time is so that it is scaled with the game engine. And so these are things we're going to be talking about in lab, okay, as we move our object wherever we want across this hypotenuse. All right, so that's kind of movement in general when we think about this. By the way, this is the same for bullets. It's the same for line of sight. It's the same for almost anything we do. We're going to use, kind of some kind of angle. And here it says, it's like how you go about calculating the slope of a graph. Yes, and it is like that. So let's go back to this. So that's kind of what we're looking at. And what we're trying to do is trying to figure out the angle in radians. And a lot of times what we want to do is we want to normalize these values, right, as an example, so that they're in, we can use a matrix. Here's an example of a matrix where we have an x and a y coordinate. And you can see that the x and y coordinate are using normalized values. When we say normalized values, whenever I use the word normalized to you, right, what does that mean? What does normalized mean? If anyone can answer that on chat, that'd be great. Think about the word or the term normalize or normalization. If I want to normalize something, what do I mean? A normal vector, okay, fine. But what does it mean when I want to normalize the values? What does it mean? Goes to 1. Yes. So right. So normalized values, what we really care about is there's two ranges that are very popular in game development. So one range is, I'm just going to put brackets here, a range of 0 to 1. Okay, that's a range. That's a normalized value range. Okay, so 0 to 1, that is normalized values. And the other normalized value range we use is, a lot of times, is -1 to 1. Okay, -1 to 1. So why do we want to use those values? Because they're easy to compare, right? So what we can do, as an example, we use normalized values of 0 to 1. Imagine color values. So typically we have color values of 0 to 255, right? So how do I convert 0 to 255 to a normalized value, right? So if I want to make a color value, let's say we'll say a color channel, right, which might have a value of some kind of value of 0 to 255, right? How do I convert that color channel to a value of 0 to 1? Well, the way you would do it is, if I had, let's just use a calculator here. I'll bring the calculator over. Okay, so here's our calculator. There we go. And if, let's suppose I had a value of, a red value of 112, right? So 112 would be the red value. That's how many, points of red pigment or red color that I'm adding to a particular object. Let's say red, this is the red channel. And how would I convert that into a normalized value? Well, I would take this and divide it by the range, the limit, the maximum part of the range, which is 255. So if I did that, then if I divided 112 divided by 255, then I would get my normalized value then would be this value right here, 0.439 whatever. And we'd probably round this up to a reasonable number. So something like 0.44 might be something that's closer, 0.439, something like that. But that would be the normalized value if we had a value of 112. And let me do that next. So 112 then might be equal to 0.439, let's say 439, right? So that might be the normalized value when it comes to, let's say, a color value, that's the normalized value. So why would we want to use that? Because it's much easier for us to have this, and especially if I want to multiply this by something else, a lot of times we use, we normalize it. Another way we normalize things is by magnitude. Yeah, so someone said that, Lewis said we take the magnitude of the vector. So again, what we'd use is the x and y coordinates, and and we take the magnitude of the vector. Remember, a vector, whenever we talk about vectors, just as a review, vectors have both magnitude and direction. So those are the two things that vectors are all about, right? Magnitude and direction. So magnitude is the length, if you will, of the vector from the origin, some origin, right? So once we have the magnitude and we have the x and y coordinates, we can then take the x and y coordinates and divide them by the magnitude to get the normalized values between -1 and 1. And the vectors, the reason why we use -1 and 1 is because what if my vector is pointing in the left direction or down, or down to the right? This is kind of up and to the right. Up and to the right typically in math is positive. Actually, if you think about this, our coordinate space in SDL is not positive up and to the right. And I'll explain this in 2 seconds again. Again, you would have learned this in fundamentals, but remember that our 0, 0 point in SDL is the top left corner of the screen. That's our 0, 0 point, which means when we go positive direction is to the right, for X, right? So that's positive direction on the X-axis. So we'll say positive X, right? And positive Y is actually down, which is counterintuitive because if you think about that, typically down means negative in our minds, right? Because of what we learn in math in school, but not so in our coordinate frames. So that's something to note that whenever we oops, that's how it normally would be. It's actually positive Y. So positive Y is down. See, I almost confused myself when I was there. So that's where that is. And positive X and positive Y, which means as we go, and why is this? It's drawn this way because the screen is drawn this way. We draw a line to the right, then we go down to the next line, we draw more, and we draw another line. We keep going down and drawing as we draw to the right. That's how we draw our screen typically. Some frameworks will use the bottom left corner, which is very similar to what we've learned in math. Some frameworks use the middle of the screen as 0, 0. Example, Unity uses the 0, 0 point in the middle of the screen. So again, it really depends on the game framework we're using. Our framework, SDL, uses top left corner, which means we have to always keep that in mind, that positive means down, all right? And if we want to go up like this, it's actually a negative Y value. Okay, that's what that is, a negative Y value. Actually, somehow my negative Y ended up there too, which is pretty cool. Because that's how it is. That's kind of negative on the way up. So this is positive, positive. This is positive on the X and negative on the Y, right? Down in here, it's negative on the X, positive on the Y, and this is negative on the X, negative on the Y up here. All right. So depending on the direction, we'll have a value that's -1 to 1, and that's why we want to normalize a lot of times for our direction. Okay. So just letting you know. I'm talking about this because we're going to have this thing happen in lab. I'm going to normalize our values. Once we have our direction in a normalized value like -1 to 1, we have a lot more control because I can multiply the direction, as an example, by the speed, and then we'll have the next pixel. So example, if we had a direction, right, let's say a direction of 0.5 and 1, right? If that was our direction, then how would that look if that was our direction, right? Well, that means we're going to travel for every speed, for every element of speed, we're going to go half a pixel on the x-axis, right? And 1 full pixel on the y-axis, right? That's what's happening. So -5, 1 is the direction of our ship that's traveling. So example, if I multiply this by some kind of speed, let's multiply this by 10, right? Let's say our ship was traveling at some kind of speed of 10 pixels per frame, right? Or thereabouts, then I would be traveling 5 pixels across the x-axis every frame and 10 pixels across the y-axis. So it wouldn't be quite a speed of 10, it'd be something else. And that is the direction really that we're looking at. This is the orientation a lot of times, and it's a value of 0.5 to 1. So that means it'd be going something like this. So 10.5 this way and then down this way. So more of a sharp angle this way. That's what will be happening, okay? Along the, on the graph. All right, so we talked about that at length. And I'm talking about these things because these are more detailed for you to understand, as opposed to when we go to lab and I'm like, okay, so we're going to travel in a normalized direction. What does that mean? Then, you know what it is because we've talked about it here in lecture. So again, when we think about movement algorithms, we want to take into account orientation, right? Because orientation is going to, the direction that the character is looking, the autonomous character, is going to be more realistic if we move along that axis, as opposed to, not using the direction or orientation at all, right? We're going to start with not using the orientation, then we'll add orientation afterwards. A lot of times what we want to do is, again, kinematics don't care about acceleration and deceleration. That's one of the differences, right? So we don't normally change velocity from 0 to 1, like maximum velocity, in instantly. That's normally not, that doesn't normally happen in the real world. But a lot of times kinematic movement is okay for us to do some of that, because maybe that's the kind of game we want to make, a very kind of retro game that doesn't use any acceleration. We're just instantly on and instantly off. Okay, but typically we don't do that these days. So one thing we also need to keep track is something called a linear velocity, right? So linear means on the x and y axis, and angular velocity, how fast we can turn. That's really what an angular velocity is, right? So the speed of rotation, or sometimes we also call this turn rate, the turn rate of an object is very good too. The faster the turn rate, so how many degrees an object can turn maximum, as an example, in one frame. I'm breaking it down like that for you, right? The faster or the more degrees of change, more degrees of rotation that an object has the capability of making in one frame is really the ability, it's angular velocity. It could be up to whatever that is, the maximum angular velocity that it can have, right? And that really tells us how maneuverable an object is in many ways, because the faster the turn rate, the higher the turn rate, then an object can kind of spin on a dime, kind of thing, kind of rotate really, really quickly, and have much different movement patterns than if it's a much slower turn rate. If the turn rate is very low, for example, let's say I can only turn 1 degree every frame, but I can move quite quickly. On my movement arc is going to be far longer and wider than if I can turn really fast. Let's say I can turn up to 20 degrees every frame. That's a huge difference, right? So we're going to see that. And when it comes to kinematics, that's how we look at it. Again, you can see that they're using something called a kinematic here in the example, where they use a position, orientation, and velocity and rotation. We've broken down our structure so that velocity and acceleration are separated into something called a rigid body, because we want to kind of get you ready for the things that we're doing in physics in the fall. All right, so that's the only difference here. These are just examples of how they would do it in the book, and there's nothing wrong with them. I think they're good examples. I'm just going to do it differently with you guys in lab. A lot of times we also there's a difference between an understanding of our velocity and orientation. So velocity means the direction we're moving in. Orientation could be the direction we're facing. All right. So sometimes we have that happen. For example, if you ever play Asteroids or some game like that, where you have a lateral slip possibility. So again, let's go back to our drawing board and let's get rid of this, make a new thing. And let's just make a very simple and dumb ship design. So we'll have a little square, right, which is our ship. And we'll make the front of the ship, like we said before, pointing to the right. We'll make the front of the ship kind of this little triangle-ish. Come on, Tom. There we go. A triangle-ish movement to the right. So this is the facing. So it's facing to the right, almost like a house on its side, if you will. And the reason for this is because if I move in this direction, I'm going obviously in the reverse, kind of reverse facing. I can also slip to the left and slip to the right. That's also possible. And especially if I'm angled. So let's say, for example, I'm angled this way. This is my spaceship. What if I drift kind of over here, right? I'm not moving in the direction I'm facing, but I do have some kind of velocity, and that can happen, right? The direction I'm facing is this way, and if I had thrust, let's say, coming out the back of my ship to move me, then I would move in the direction normally I'm facing. And so that motion that I would have, and we're going to talk again about motion in natural motion, maybe in physics, is I would kind of move here, and then when I'm turning, if I turn this way, now I'm moving in this direction, and then I'm turning a little bit, and then I'm moving in this direction. So you can see, depending on my turn rate, that particular frame, it's going to influence which direction of motion I'm taking, and my velocity will change. Okay, so that's the kind of idea, right, where I'm moving in different directions. So again, they kind of are independent, right? Velocity and orientation. I might have a lateral slip from a velocity perspective, even though my orientation is facing forward. Okay, if I have in physics, I might be able to impart force in a particular direction, even though I'm facing in some, and maybe my facing will be or my orientation will be different. So, example, going back to the graph, right? So if I was to, let's just undo. Oops, let's redo. um, So let's suppose that I push my ship in this direction, right, with force. So I'm going to start drifting this way. But then what's going to happen is I can also change direction while I'm drifting this way. That is also a possibility, and we see that in games as well, right? So where we kind of use forces to push or move my ship around. And you can see that that's the exact way that they're showing it here in this picture. So we start off frame 1 pointing in the northerly direction. And then in frame 2, we turn. That's a pretty good turn rate that the object can turn this much, right, in frame 2. Notice that it's also offset from its original location here. And then in frame 3, it's moving here. And in frame 4, it's moving down this way. So you can see the direction it's going to take is gradually changing based on its orientation. And that's a nice way to do movement, as opposed to slipping to the right and left, and unless that's the kind of game you want to make with some kind of physics forces. So we want to be able to update our position and orientation every frame, and they give you a little formula on how to do that. Notice what they're doing here is they're saying, hey, let's take our current position, and add velocity. So this is your formula, and we're going to use this more in physics. And what they do here is they multiply velocity by time, and then they're adding 1/2 of the linear acceleration. That's what this is, really. Multiply by time and then time again. And this formula is really the kinematic equation that we're going to learn in physics next semester, which is, let's see, go here again, and I'll try and type it out for you, your final, so let's say position final, right, is equal to position initial, right, plus velocity initial times time, right? I'll make them all capitals for now because I have limitations here with what I can do. Plus 0.5 or half your acceleration, right? And then t squared, which is looking like this. If I can do that, let's say that's square. So that's, and a lot of times we say p naught t plus v naught t plus 1/2 at squared. And that's kind of your kinematic equation that you may have learned in grade 12 physics, let's say, or grade 11 physics, depending when you took it, which gives you a parabolic motion, kind of when it comes to movement. If we apply the position for both x and y coordinates, then we get a lot of times a parabola, right, of motion when it comes to, especially when we add acceleration, which is based on gravity, we might get a motion that looks kind of like this, right, when it comes to, this equation, right? But for us, instead of using a motion like this, we can use this equation, to move us in the direction we want to and accelerate, as we go. Originally, when we did physics a couple of semesters ago, we also learned about calculus. And one thing we learned about calculus is we can take the position equation and we can derive velocity and then further derive acceleration. So that's something that we're going to be looking at further. So again, don't look at this as pi, but position initial, position final, velocity initial times time, and then 1/2 of acceleration times time squared. And that's what we're showing really here, this kind of thing where my position is, we take the initial position, add plus equal, which means add so position is equal to position plus velocity times time, right? So this time equation usually comes from delta time, or the time between ticks, of the clock, which is our game clock. Our game clock basically is, 60 frames per second, which works out to be 0.0 or 16.6666 milliseconds, right? So that's kind of what it works out to be. And we take that, and if we scale our velocity and our linear drive by by time, then we get a really smooth looking and realistic looking equation or movement. And same thing with orientation. Orientation is kind of multiply, you take the rotation and the rotation angle multiplied by time, and then we take the angular velocity. So this is the linear velocity, and this is the angular velocity, and we take the angular velocity multiplied by time. So kind of interesting. And that's how we can do kinematics. We're going to do this slightly differently in our framework, but for the most part, that's how movement happens. All right, and so this way we have I'm going to skip through this for you to read. This is how we move things around in our autonomous characters so that they're realistic, even if we're using kinematic equations. We're not accelerating, we're instant on velocity, instant rotation, and those kind of things. Forces. One thing we're going to learn about next semester is Newton's laws of motion, which really apply to video games a lot. Newton has 3 laws of motion that we're going to be talking about. And really what it is let's talk about the first law. For every, if an object's at rest, it tends to stay at rest. If an object is in motion, it tends to stay in motion. So that's Newton's first law. Newton's second law is force is equal to mass times acceleration. So it equates force. Acceleration is directly proportional, to its mass, right? So if I have more mass, as an example, and then the amount of force that's required to push an object, to a certain velocity, or to accelerate an object to a certain velocity, the amount of force required increases at the same rate as, as an example, or related to the amount of mass. And this equation here is the thing that stops us. I like to say this in physics, stops us from reaching the speed of light, right? Because if you think about the amount of force, one thing that Einstein talked about and we'll talk about that more in physics, is that mass, as we approach the speed of light in a vacuum, then mass increases to infinity. So if you imagine that if my mass keeps increasing as I increase my speed, then the amount of force also increases to infinity, which means we can never reach the speed of light using Newton's laws. Anyways, let's continue. So Newton's third law is for every action, there's an equal and opposite reaction, right? That's kind of a layman's way of saying it. And so that we use Newton's laws for motion. We use Newton's laws for collisions and reactions to collisions. We're going to talk about that again more next semester. So I'm going to skip this slide here and go to, it talks more about how to do motion. So one thing we're going to talk about is this idea of steering behaviors, right? And when it comes to steering behaviors, what we want to try and do is steer our autonomous character in a particular direction. And there's different algorithms. We talked about algorithms for movement. We can apply different algorithms to steer our autonomous characters in a particular direction. So we have this thing called kinematic seek. And by the way, if you look up steering behaviors, let's do that together here. So if I say steering behaviors, let's put it the American spelling for now. There are some great articles on steering behaviors, and there's actually some old articles. This is the original white paper by Craig Reynolds that he posted, and it talks about pretty much all the steering behaviors that are here. And for example, he talks about seek and flee and what those look like. So let's look at steering behaviors for autonomous characters. Hopefully we can get to that. Maybe not. And again, sometimes this happens with everything. But at the end of the day, what this does, there's different steering behaviors. So there's seek and flee, pursue and evade. And unfortunately, it doesn't really show the images here as I would like. Wander, arrival, obstacle avoidance, containment, wall following, and a bunch of other stuff we're going to be talking about. Those are all part of the steering behaviors that that typically that you'd see in this white paper by Craig Reynolds. See if I can get this somewhere else, and if I can look at the full article online. Here we go. Okay, so here's the full article. So so basically, what we're going to be talking about is an object, okay, that has thrust. Thrust comes out the back, as an example, and we're going to use steering, to move an object forward. And this is a great little paper. I'm going to include this one, and this is from GDC 1999. I'm going to include this inside of as a link here that I'd like you, if you're interested. I think it's a good link to look into. So we'll talk about steering behaviors article, right, that you can look up when you have the time. I think it's an interesting read, and it's a lot more details than I've included in the PowerPoint because you don't need it all. But I think it's really good to take a look at this. So if you notice what seeking would look like, if I have a target, the seek algorithm would kind of go towards the target. And notice it's going to go in this arc. Why? It's going to go in the direction that it's looking. So that's kind of the way it works in this particular thing. So that's the seek path. And the flee path, take a look at the flee path here. The flee path goes in the opposite direction. So if this is the target and this is the ship is going to go in the opposite direction for flee. So that's steering behaviors, the two that we're talking about here. And notice that they have things called the desire velocity for seek, which is a vector that's directly pointing at the target. That's a desired velocity, right? And this is the current velocity. So I'm going in this particular direction, and I have this vector that changes every frame, right? To give me this arced movement as we're moving towards the target based on the function. So this old article, if notice what it says here, desired velocity is equal to the normalized value of the position minus the target, right? Multiplied by the maximum speed, whatever that maximum speed is, right? And steering is the desired velocity minus the velocity, the current velocity. And so that's the steering. And those are the two values that you'd use, for seek, okay, as you move towards this. We're going to have these values, we're going to use these values when we do our lab later on today. All right, so so they have in the book that we're using, they use this get new orientation function to face in the direction that we're moving. And so here is what kinematic seek looks like, where we kind of get the, I'm not going to go through all the pseudocode here, but again, the idea is the same as we saw in the article. We're going to get normalized velocity and multiply it by the maximum speed, and that is going to be the velocity. And the orientation is we're going to get the new orientation based on the direction, the desired, direction that we want to move in. And that's really the seek algorithm. What happens with the seek algorithm? And let's see if I can get a graphic for this. So if I do seek algorithm, and let's kind of look at that steering behavior. What we also can look at is some images for that. So it talks about, there's a lot of them, right? And one thing to note, I want to see if there's one that's more of a GIF, animated GIF. See if we can get that going, because I think it's kind of neat what it does. I'm not seeing something though. Here we go. Just want to see what seek looks like. There we go. So see, this is kind of the target, and then these are kind of seeking the target. And notice these wobblies happening. The wobblies are happening because, and this is kind of flocking behavior as well. We'll talk about flocking and later on. Wobblies happen when you're changing the values on a very quick basis. If we want to try and not do that, here's some. See if we can get another one when it comes to seeking behavior. So steering behavior or seek steering behavior animated GIF. See if there's another one like that. Yeah, so that's kind of not exactly what we're looking for. But anyways, we'll do it in class. But the idea is that is how it works. It kind of seeks towards the target, and we use this idea of we have a current velocity, which is remember velocity is a vector, so we have magnitude and direction, and now we need a desired velocity, which has a new magnitude and direction, and we're going to move towards there in this kind of arc, based on the current on the orientation that we have right now. All right, so that is seek, and there's also flee. The flee modification is basically we reverse the direction. So the desired velocity is literally we multiply by -1 for the most part, and we go in the opposite direction of the seek direction. So we go this way across the other path. Again, we have the desired velocity is flipped. So instead of going this way, now we're going over here. And we have our current velocity and we have a desired velocity, and now we're moving this way. Okay, so that's flee. So flee means I would use flee if I was for an autonomous character. If I was fleeing, as an example, the player. So if my target is the player and I want to try and seek to the player, maybe this is a missile or some kind of missile weapon, a bullet or something that's a seeking bullet. It could be also the autonomous character themselves seeking after the player, right? So chasing, if you will, in some ways, right? And as I'm chasing or behind the player, this is kind of a basic movement, and we're going to learn seek a little bit of how to put together seek today in lab. All right, so that is flee and seek. We also have other steering behaviors. One of them is called arrive. So remember, we just said that seek, what happens is we kind of seek towards the player, but it keeps seeking, which means that if I pass through, if I have a velocity that's going to carry me through the target, I'm going to come down here and then turn around and come back. I'm not going to stop. My velocity is not going to reduce, right, when I'm moving. So again, as I'm moving towards the target, I come back and I keep moving towards the target based on my current velocity and turn rate. And then I move back towards the target and I keep moving around the target over and over again, forever. And the reason why this happens is, because we don't have a slowing down. We keep going with our maximum speed constantly. So arrival, which is what we're talking about here, actually slows down based on the distance to the target. Usually what we use is something called a radius, right? And the radius, as an example, is something that we use to slow down. So let me show you what that looks like in our graph. So again, let's just undo some of these changes. So let's say we have our ship and we have our target, right? So let's say we have our target over here, right? Way over here. And we have our ship over here, right? So again, what we want to do is we want to move towards the target. Well, if we're moving laterally this way, so it's kind of going toward the target, we're going to move towards the target. And then as soon as we slip by the target, then what we want to do is immediately kind of turn around and go back around maximum speed again. So you'll see seeking behaviors kind of work like this. They flip around, and then because a lot of times we have, this kind of stuff, it'll keep on going back and forth, right? So that's seeking behavior. But arrival, we want to place an imaginary radius around the target. That's typically how we do it. All right, so let's suppose here's the target. We make a radius around the target, let's say something like this. And then as the player or the autonomous character moves towards the target, when it hits this place right here, it starts to slow down until it hits the target and stops. Okay, so that's when it slows down. So it's almost like a deceleration that when you hit this radius, that's how it normally goes. Okay, so that's the way the arrival works. So this is, for arrival, we modify seek. We still do seek, but we slow down as we approach the target. And our pseudocode is here on how to do that. We create a radius, and we also kind of, for kinematic arrival, we use a time to the target. We figure out how long we want for the target, for us to reach the target, and we do it the other way around. We calculate the exact time to the target based on, kind of we reverse engineer how long it takes to get there, as opposed to, slow things down. Because there is no deceleration and acceleration for kinematic arrival. Okay, we don't have that. We just have what's the time to the target. I'm going to get there in that time. What's my new velocity? My new velocity based on the time that I specify to get to the target, and that's how long it's going to take me to get there and slow down, right? So it's kind of a very simple way of doing things. So that's the arrival algorithm. And if you look at the document that's up here, then arrival looks kind of like this. So as you see, we're kind of heading towards the target, and as I hit a radius, I keep slowing down until I stop. That's kinematic arrival, or arrival in general. And it has the arrival algorithm right in here. All right, so that's why it's important to have these basic algorithms, because this white paper, is a lot of the stuff we get from our book and from other sources really reference this article. This is kind of the original article that we use over and over again. Okay, so that's kind of arrival. That's what arrival looks like. All right. Then we have the wander algorithm. A lot of times what we want to do is we want to give a flavor to the way an autonomous character will meander across the screen. And what happens is it's going to take a random direction. There's going to be a bit of stochastic or randomness, I would say, for the way it works. So it's going to kind of, wander to the right and then maybe wander a little bit to the left. We don't want the wandering algorithm to happen every frame again. We want to move for a little bit and then change slightly the direction based on the turn rate, then move in that direction for a little bit, then change slightly according to the turn rate, some random direction in front of the character. And it keeps doing that, and it creates this wandering algorithm. So it looks like the character is moving in a weird random direction. And this is kind of neat because, especially if we want to create the illusion of a thinking character, we don't want always a straight path, as an example, for the character to move. So that's wander. And there's the wander algorithm right there. So here they don't talk about wander, but they actually talk about a couple of additional things. And we'll talk about that as well today. One of them is pursuit, and the other one is evasion. So those are a couple of additional steering behaviors. So pursuit is like, okay, so this is where my target is right now, and we call this the quarry. So let's suppose I'm hunting. My ship is a hunter, my autonomous character, and I'm pointing in this direction. This is my current velocity again, and here is the quarry kind of running towards this direction, and this is where it's going to be in the future. What we do with the autonomous character is we cut the character off, the player, and meet the character where they're going to be, right, based on the current velocity of the quarry right now. And usually we try and do that by calculating how many frames, and we keep trying to pursue based on the new current velocity of the player or the target, whatever that is. Evasion is the exact opposite. So if this is where the quarry is going to be, we want to get out of there. We want to go in the exact opposite direction, and we want to calculate where it's going to be in the future, and we want to calculate a trajectory that is directly opposed to where this is going to be in the future. So if this is where it is right now, what we want to do is we want to angle away from it because we calculate that this is where it's going to be at some other time t. Okay, so that is pursuit and evasion. And again, we talk about it here a little bit in, we might talk about it here a little bit in thing. But so all we talked about here is a couple of things: pursuit, seek, arrive, and flee. But I also kind of talked about this idea of pursuit and evasion. And we're going to talk more about pursuit and evasion with dynamic behaviors next week. Because we talk about kinematic this week and dynamic next week. That's kind of where we head off, right? So kind of really neat in terms of the type of behaviors. This article and we're also one of the things that we talk about in your assignment is this idea of obstacle avoidance. One thing you have to do in the assignment is do obstacle avoidance. And how do you do that? A lot of times, what we're going to talk about in the future is this idea of different feelers that we kind of have coming out of your autonomous character, and these feelers, right, or whiskers, if you will, allow us to move the character so we can avoid obstacles. And obstacle avoidance is a key when it comes to AI movement, because we don't want the AI to go through an obstacle like a wall or some other target. And so this is one of the things that I'm asking you guys to do in your assignment number 1. All right, so this is kind of the most difficult piece of assignment 1. Nahar says, if you wanted to make AI stop a little further away from the target, would you need 2 circles? Yeah, you could. One to slow down and one to stop. Absolutely, because you'd have a new target, really. You'd have an offset from the target. So that's what you'd want to do. Okay, so again, so these are the kind of things we've talked about a little bit, here, and kind of cool. There's other things we're also going to talk about. One of them is next week is going to be called path following, where we have either a linear or curved path. And what we want to do is we keep our distance, again, from the path by some number. So we have some kind of path target, a target to the path, and we're following along the path based on the target. All right, so that's kind of neat, path following. There's wall following, where we follow along the wall. There's also something called flow fields, where you have a bunch of vectors. And what happens is the target moves along these flow fields. Think about this as water flowing, which is kind of neat. And a bunch of other things, right, that it has, right? Where we move into when we talk about steering behaviors is something called flocking, all right, which is kind of neat. And we can use these same things, that we talked about. We'll talk more about flocking next week, right? But really what we talk about is once we have basic steering behaviors, we can use multiple autonomous agents or characters, AIs, that kind of know where the other one is. And so they move together in a flock that we'll talk about next week. All right. So, and there's different aspects. One thing we're going to be talking about next week is separation and cohesion. Separation is the minimum distance between objects, and cohesion is the maximum distance away from an object. So we kind of stay together, but don't touch each other. That's the kind of thing that we use. We also use something called alignment, where alignment is moving in a particular direction. Again, these are all things that we're going to be talking about, and alignment's based on a leader that you're following. So that's kind of flocking behavior, and we talk about this again more next week. We can also combine behaviors together, where we use kind of fleeing and an arrival, pursuit, different things like that, where we kind of combine behaviors to make more complex movement. So again, great little article. I highly recommend you take a look at this. There's a lot of really good details here. Again, it's a little old, but it doesn't matter because it's the exact article that most books reference when it comes to how we move things, autonomous agents around the screen. So questions around steering behaviors, right? How this works. Again, think about this steering as path determination, and what the difference between locomotion is and animation. That's something also we can ask. So here's something. What is the difference for you guys between locomotion and animation? Anyone have an idea of what that is? It talks about locomotion here, but it also talks about animation and articulation. But does anyone have a difference? If I was going to say locomotion, what's the difference between locomotion and animation? Anybody? You can put it in the chat. Yeah, so Nihar says locomotion is like kind of moving. And what's animation then? They're kind of both movements, but what's animation compared to locomotion? They're different. Just the look of it. Well, think about, I always look at, locomotion. If I was going to define locomotion for a second, is, going back to this, let's suppose you have a ship again, a ship object, and here, we'll do this. And the ship object is moving. So locomotion is just movement. This is locomotion, right? Animation, maybe we're going to have inside the container of the ship itself some kind of movement in here. Like, let's say, for example, if the ship had wings, right? And the wings would kind of move as it was moving forward. This movement of the wings, this animation effect, that'd be something that's contained in the character itself, right? As opposed to changing position of the character. So think about the game object then as a container. So imagine this is the game object, making it big, right? And inside the game object, you can have motion inside the game object itself relative to the the parent object, right? And inside the game object, you're going to have animation or movement, right? But locomotion means this whole game object container is moving forward, right? A good example of this is if I take a character like a humanoid character and I just move them around the screen without moving their arms and legs, that's locomotion, right? But if I move their arms and legs, as an example, and I don't move them around, I might have an animation. And a good example of this might be something like an idle, right? So one thing we're going to be talking about later on in our time together at George Brown, if you go to something called Mixamo, right? Mixamo is kind of a free character generator by Adobe, right? Which is kind of cool. Now, they make you log into an Adobe account, which is kind of cool. And let's see if I can do that. If it remembers who I am. Yeah, it does. So that's pretty cool. So there's Adobe. And what it does is you can pick a character here in 3D. And when we do 3D games kind of in the future, and here's our little guy that I picked last time. Let's pick another character, as an example that's not as weird looking. Let's pick this dude right here, right? So I'm choosing the character that's different. Now you can see that this character is in T-pose, a different kind of character, right? There's the character in T-pose, right? And right now this character here is, not moving. There's no locomotion. But let's suppose I want to add animation. So no locomotion, but animation, right? And let's do an idle animation. So I can type in idle, right, as an example. And let's just choose an idle that makes sense, right? Maybe he's going to idle, like this. You can apply the animation. So you can see that there's no locomotion here. The character is moving, right? There's animation, but there's no locomotion, right? So the character's not moving away from its position. That's the difference between locomotion and animation. Animation is in the character itself, and almost like this, if you think about this cube where the character lives inside this cube, almost like a bounding area, the animation happens in there. Locomotion is me moving that whole bounding area, including the character and any animation related to it, in another location. All right, so that's kind of the way that it works, right? And again, this is a neat little program. You can try it out later on, and it's online where you can apply any kind of, animation to it. This is where, let's suppose the character is holding a rifle or some other kind of weapon, or if he's some kind of ninja, where, they're idling in a different spot or whatever. And you can download these little animations and implement them in Unity or Unreal, as an example, in a game engine. Later on, we might even do it in our own game engine. Not this semester, but it might be another semester where you learn how to do this. But again, this is the animation. That notice there's no locomotion. Whereas if I have a run animation, let's say for example, so here's a running animation, and now we have both locomotion and we also have animation. So where the actual character is moving from one position to the other, and this is a loop. Right, and an example of what the character would do when they're moving, right? It's not a great little running animation, but what you can do is you can move it in place. So there's the same animation, right, where it's moving in place. Again, animation, but no locomotion. All right, so this is an example of how that would work. All right, so that is some examples of that. And we're going to be talking about throughout the time here at George Brown, we're going to be talking about this kind of idea, for different characters we make in different games. Again, I will also invite you to look at other examples online. So if you look at things like flocking, so what does that mean? So, when it comes to steering behaviors, so we're going to look at flocking, like I said, more next week. There are some great videos that exist out there that show you what flocking looks like. Now, I'm also recording this on YouTube, so really, I shouldn't really show you this stuff, but I'm going to do that with no sound, and you can see what the flocking would look like. Again, I'm using a video. I'm not monetizing this, so it should be okay, but you can see what that looks like, where you have a groupings of agents running around the screen, and what they're doing is it looks like flocks of birds, right? So that's kind of what it looks like there. And that's an idea of flocking, but they're using the basic steering behaviors. They're looking at arrival, or they're using seeking behaviors as an example to move in the same direction. And the same thing we can do with some kind of seek behavior, so seek steering behavior. Take a look at that as well to see what it naturally looks like. And what we want to try and do is as much as possible, what I want you to do is if you see, kind of an example of that, right? And let's see if there is, trying to see if there's an animated GIF again for seeking. A lot of times what they have is, let's see if that's an actual thing. There we go. So there's your seeking behavior, and there's your fleeing behavior. Notice that it's not complete because seeking behavior should go right through the target as an example, because it doesn't stop there. There is no arrival. The target, your object is not slowing down. It's continuing the same rate of speed as it was going before, right? So that kind of stuff. All right, that's enough in terms of the stuff I wanted to cover today. We're ending a little early today because we're sitting at this part. So one thing I wanted to cover again with you before we stop today is the assignment 1 requirements. Okay, I want to talk about this assignment 1 requirements one more time because I think it's important for us to not lose track of what I've asked you guys to do. So let's take a look at assignment 1 one more time. Now that you know what those behaviors mean. Last week we talked about it really briefly, but we really didn't go into a lot of detail because you didn't know really what seeking behaviors were. You could have looked them up, of course, but think about what it says now in terms of the behavior. So seeking, 10 points. When the user presses the number 1, and I'm going to put this in there for you guys in your mind, instead of pressing number 1, if they have if they're pressing a button in IMGUI, a target sprite will appear somewhere on the screen, and this could be random or not. You can make it so it's fixed, and an actor sprite, ship, vehicle, or whatever, will enter the scene from one of the edges and seek to the target using the seek algorithm shared in class or one that works better for you. So this is something we're going to talk about today, right? One thing we haven't talked about is this idea of look where you're going. The look where you're going algorithm is, changing our orientation so that it's, our autonomous character or our actor is moving towards the target. That's kind of what we want to do. We also have fleeing in there for 10 points and arrival. Arrival, again, sprite will appear, and you're going to use the arrival algorithm, which kind of adds on to the seek algorithm. So arrival is really a modification where we start slowing down when we come closer to the target. The big one, and I got to be honest, is this one, obstacle avoidance. And the way to do obstacle avoidance is to have some kind of whiskers for the target. And if I was going to draw those out for a second, let's go back to our target and our ship. Okay, so let's go do this. So I want to, in this scenario, I might have let me just move this around a little bit to give me more room. So let's suppose I want to go to the target. I want to seek to the target now. But instead of going forward, I can't because there's some kind of obstacle in the middle, like this, right? So how do I move around the obstacle? We're going to be talking about that over the next week or so. Well, I need to be able to know that there's an obstacle in front of me, right? I need to know that. And so what you could do is you could extend whiskers, right, in front of the character. There's a couple of techniques that we can use. So a whisker that kind of comes in front, a whisker that is, over here, and a whisker that is over here in some kind of detection radius. So why would we do this? Because if we just had one, right? So if we just have this one, so some kind of line of sight or a whisker that kind of is an offset from the character, and if we did that, and if we were trying to turn away, let's just get this whole thing happening here. So I'm going towards the thing, and before I get there, I turn. So watch, I start turning, right? And then I move forward, and I start turning. Depending on my speed, right, I'm still turning because I'm still colliding. And now I'm turning and colliding, okay? And you can see that depending on what's happening, because I only have a single whisker, then I'm probably going to still collide with the object, right? Because depending on my speed, I might still do that, right? I still might collide with the object because of the single whisker. I can't detect when I'm clear, right? But if I have more than one, right? And this is just one way of doing it, guys. There's more than one way of doing this thing. All right, so this is a couple of ways to do it, and we'll talk about the other way as well, because I want to help you with your assignment as much as possible. So here's where we're going to go forward. Now we're starting to collide. We turn, right, and we kind of go forward, and now we see that we're still colliding. So we turn more, and we turn more, and we keep turning more, to avoid collisions altogether. Notice that that whisker is still colliding, right? And so what we want to do is get away from this thing as much as possible. This whisker is going to help us navigate around the object a little better. So this is definitely one way of doing it by using whiskers. The other way of doing it is not to use whiskers at all, but actually to use a radius, right? So what you can do is you can put a full radius around the ship. Oops. Here. I'll be okay. There's the ship, and let's suppose this is the radius around the ship, and let's move the ship around with the radius instead. So the radius obviously is not drawn. It's something that is there. So I move forward, and as soon as I kind of collide, I start moving the ship. And as long as the radius, the circle, is colliding with the obstacle, I want to keep turning away, right? So that way, and I'll keep turning away, by the way, until I'm clear. Right? And then what I'll do is when I'm over here, I'll start turning back, right? And I'll go along the path that I'm pointing until I move around to get to the target. So that's kind of some way of doing it. A radius is also another way of doing it. Nahar says, is that more expensive than the rays? Well, it's still collision detection no matter how you slice it, whether you're doing a ray or whether you're doing kind of a radius. It's really up to you. Other techniques I've seen in the past by students, which are very interesting, is where I have a ray that goes forward here, and then at the end of the ray, there is a circle. So something that looks like this, right? And the same thing goes with the whiskers over here. So you have another whisker over here and another whisker over here. And they did this because it's almost like they have these three circles that are, I would say, invisible. All this is invisible, of course, right? And why would you do this? Well, because what you can do with this is very similar to the circle idea. This might be in many ways more accurate or provide a different movement capability for the ship. Because again, think about this. Now you have a radius. So I start hitting it there, and then I turn, right? And then I move, right? And then I turn, right? And then I maybe turn more because of this little thing. And you want to kind of slow down. What you can do, one of the tricks to do is when you start, kind of hitting an object, what you do is you slow your speed. You don't go at the same rate of speed around an object. You slow it down, almost like using the arrival algorithm. But here, notice that when I'm slowing down, depending on the angle, I came right in the middle of the ship, the obstacle, as an example. Then I want to turn, right, as much as possible away. So you might see a bit of a turn like this. And then as soon as I'm clear, you wait X number of frames, and then you start turning back, right? because you want to clear the obstacle before you move forward. Okay, I'm just showing you a very rough idea of how it works. It's very similar to the whiskers idea, but the circles make it easier sometimes from a collision detection, because circle and rectangle collision is easier sometimes for some people to pull off than line and rectangle. But I've given you those things. I've given you all these kinds of detection techniques as well. Another thing to do, and this is one more thing I want to talk about, so that way you guys are good. Okay, let me do this for you. So instead of this all together, this idea, what you do is instead, every obstacle has almost like little nodes. Okay, so imagine if every obstacle had these invisible nodes. Let's make a different color for these things, so that way we can see what those look like. So let's make the color of these little nodes a different color of blue, right? So make it like that. And so let's say we have a node that is here, and we have a node that is here, right? And then maybe a node that is here and here. The obstacle itself is associated with a bunch of these nodes, right? And each of these nodes might be kind of hints for the player, right, to move to, as opposed to the player itself, kind of figuring out how to move around. You can use these little targets, new targets, to move around the obstacle as well. It's almost like a cheat or a hack, if you will. And I've seen people do that as well with their behavior. I think it's more expensive, but people do what makes sense to them when they program. So let's say again I have array. Let's try that again. Let's say I have array that comes from the ship, right? And let us draw that ray. So again, as I move and I hit this ray, right? This I keep going through it. I don't care. I know the information that the ship has, even if I'm here. Maybe I'm at this point here, not actually passing through the node. But let's say I'm here and I'm passing through and I hit the kind of the obstacle. Then now I have some options. I can go to the nearest node that has no collision. I can start turning my trajectory away. So now my target is this. So I move to that particular location, right? And then what I do is I follow to the next location and the next location until I'm clear. And once I'm clear of the target and my velocity is the way it is, I re-angle towards where I'm supposed to go, my target, and then I move forward this way. So that's also a way of doing it, where you create almost like a set of nodes around each of the obstacles. Now, again, it's more expensive but what you're doing is you're giving the player or the autonomous character a path to follow, as opposed to them trying to do it dynamically. So again, there's different approaches. To me personally, it doesn't matter how you do it. I think it's important that it works and that you don't collide, right? So that's something that we're going to be talking about next week in more detail. All right, questions around the assignment details, because the assignment is coming up, guys, and I need you to start it. All right, please don't wait till the last minute to do this thing. This is not something you can accomplish in a day. You need to do some trial and error. There needs to be some stuff that we have you do. And this is individual. You're not working with anybody else on this thing. This is your own code, well, using the assignment framework, of course. And anything I share with you is fair game, right? Like if I share Seek with you as an example, that's okay. I've shared it with you. That's no problem. But please, what I'm asking you to do is you're not to work with another person in the class on this, because when it comes to working with others after this assignment, you won't be able to contribute anything if you don't understand how to use the framework. So this first assignment is really, how do I use the framework? How do I do some basic movements? And so that way, when it comes to something more complex, like for example in assignment 2, then you can combine with one other person to make something that's more a little bit more challenging than this. This is kind of the easiest level. Steering behavior is kind of the lowest thing you can do. One other thing to note is, so that's assignment 1. Again, that's due next Sunday at midnight, not this Sunday. But one of the things to note is that on Blackboard, right? And let's go to Blackboard for a second. If you look at, I've created a bunch of groups, right? So here's some groups. Some people have enrolled, right, in groups, but not many. These groups are for assignment 2, right? So start thinking about who you want to work with in assignment 2, right? Because assignment 2 is around the corner too. If assignment 1 is due next Sunday, next week I'm going to give you the details. I've actually already released the details for assignment 2 here. This is assignment 2, and this is due week 6. So this is going to come at you pretty fast and furious. And pathfinding, even though it uses a group structure, I highly recommend you sign up for a group now and you start figuring that stuff out. So by the time you start working on assignment 2, you already are in a group. One thing to note is you cannot be a group of 1. Okay, you cannot be a group of 1. I won't allow it. And if I have to, I will assign people. I don't want to do that, and that's usually catastrophic, because if I assign 2 people together and if you don't like the other person and that person doesn't do anything, but you're assigned to be with that person, and if he doesn't do anything and it's hard for you, you're going to get 0 too. So I wouldn't prefer that. I prefer that you find a partner on your own. And so I'm telling you here at week 2 that you need to do that. Don't wait until week 5 or week 6 even to find a partner. You cannot do this thing on your own, and it needs you to sign up, to groups in order for you to see this assignment in the first place and do it. So please sign up early and choose a partner that you know is going to work. If you think that partner is not going to work or cannot work, maybe you don't want to choose that person. Maybe they can't work with you. But guys, it takes effort for you to do this stuff. So please, start thinking about a partner now. Okay. Any questions around assignment 1, groups for assignment 2? We talked about steering behaviors again, as an example for what our topic was today, steering behaviors, which is just and kinematic movement. And next week, when we get together, we're going to be talking about more advanced steering behaviors and collision avoidance. So those are the 2 things we're looking at for next week. But again, your assignment's due at the end of the week. So start assignment 1 now. Don't wait until, because you have all the tools really at the end of the day you need to get going. You don't have to wait until next week to start. That would be a bad thing to do. How many people can be in one group? Well, let's take a look at the assignment details. So if you look at the assignment details for A2, right, as an example, if I'm not wrong, you have a choice of you and a partner, like 1 person, so 2. A group of 2, I think, for the first assignment, right? 2 members. So that means you and 1 other person for assignment 2. Again, June 20th looks like it's far away. Guys, not far away. It's around the corner, right? It really is. And it's going to come at you, because you have other courses that you're doing as well. It's going to come at you fast and furious. Start thinking about who your partner is going to be way ahead of time. All right, so that's really it for me today. Let's again, we're gonna meet again, in another hour and a half or so, because our first lab, if we look at our first lab right now, is 11 a.m. right? So that's for lab 1. So from 11 to 1, and then our next lab is from 1 to 3. So I'll be recording the lab from 1 to 3 again. And remember, for those people who are joining late, let's say this is your first week, if you look up on Blackboard here, right, all the details for the labs, if you look at the lab as an example, lab 2, I've already updated. I'm going to be using the new, kind of this new object called an NCL. It's just a little ship that we're going to use for this lab coming up, because I'm going to use a different object. We're going to make a brand new game object for our lab 2. And again, you can see that this lab is going to be due Sunday at midnight. That's this Sunday at midnight. Each lab is worth 2% of your final grade. And you have to complete 10 out of 12 labs in order for you to get, kind of your maximum grade for that. Some people last week, I have to mention this as well, when they handed in their lab number 1, they didn't give me a valid GitHub repo. They didn't include me. They made it private. and all that kind of stuff. Please, if you're going to make it private, which is what I've asked you to do, make sure that you include me in your lab as in your project as a collaborator. Also, other people had badly formed repositories. They had a zip archive that they uploaded on their GitHub. That is not the exercise. Okay, uploading a zip archive on your GitHub repo is wrong. It's not the way we do things. We upload the files, not a zip archive. Okay, that's not what I've asked you to do. And also, they've given me some other work. For example, you're giving me some work from another course on your GitHub repo. Yeah, that's not acceptable either, guys. It has to be the work from this course. When I've asked you for screenshots, make sure you give me screenshots from this course. And make sure you give me screenshots that show me that your application is running, not your code. I don't care about that. And please do not, whatever you do, some people do this too, please do not submit videos for your lab. I don't have time to go through videos for every lab that you submit from now until the end. It just needs screenshots, 3 of them. All right, so please make sure you adhere to those requirements. Anyways, I'm not going to keep you any longer. It's 9:30. I want to let you go a little early today, and I'll see you guys at 11. Otherwise, are there any questions before we go? Thanks, Lyra. All right, hopefully I'll see you in class. Bye, Hassan. I'll see you guys in lab again at 11 and at 1. Thanks so much. I'm going to stop the YouTube stream now.